Okay, cool.
How hard do you think it'll be next semester? Like, I don't have the least of the next time I'm doing it today that bad to forego year.
No. Do you think you're going to put it off a whole year and then start up after
Or
that?
I would like
They
to do
have
it next
Orgo 1
fall.
offered in the spring.
Yeah,
So, okay, I see what you're saying. Yeah,
yeah,
that's
like,
what
I
exactly what you
want to do
said.
it, like, I'm
Mhm.
like memory,
It's
but I
really
can't.
different. So it's so different that like you'll be fine still, even if you take it the next semester. There's really only a few things you got to hold on to. Acid-base chemistry is actually the most important thing for Orgo, but you're going to relearn all that stuff, and they're
Yeah.
pretty nice at kind of like they don't expect you to have it all 100% down. They will review it with you, so you'll be good.
It's really cool behind it.
I think it was similar like difficulty, but like it took more time. It probably demanded the most like day in and day out work. Whereas this class, you can kind of like maybe get by with like cramming the last couple days. Orgo, you do need to keep up with every day. Um, but it's cooler. It's way more exciting than this. And most you don't care. Yeah. You're not going to be worried about that. It's fair. Are you pre-med or pre
I'm health science.
health science?
Hopefully CDC eventually. So,
Okay. Okay, cool. Nice.
yeah, but
All right.
yeah, it's not fun.
That's a lot.
Not pre-med, so I can't play.
Got it. Yes. Yeah. I am. Yeah.
What classes do you stuff?
I've I've been done this whole year actually. I'm basically here for vibes. It's kind of nice, yeah. I wrapped it up last semester or last spring with animal physiology, which is the hardest class. I picked up the biochemistry minor, and so we're kind of completing that. So I'm taking some extra chemistry classes and then a whole lot of random electives. Like I'm taking
It's like
I'm a senior. Wait, what's that?
fifth year. When you said
No. I'm a fourth year. I came in with some credits, so I was done with all my gen eds sophomore year. Yeah. Yeah. Yeah.
Next. I'm freshman. I can technically graduate in a year, but I was like, I'm not planning.
I would not do that. I love being here and like I have a few extracurriculars I wanted to keep up with too. So like I was in no hurry to get out of here. I had to take my MCAT last semester anyway, so like yeah, I do. Yeah, I know. It's my last semester. It's kind of sad. No, it'll be a whole year of applying, but fingers crossed UVA is the goal. Would love to go there. We'll see. It's very hard to get in, so I'm not gonna get my hopes too high. Yeah. Oh, well, thanks. We'll see. I'll have I'll keep you guys posted. I'll still be here. So if you guys Blumley one day, he'll know. All right, we can get started. All right. So yeah, we learned about buffers. Does anyone want to say the two main definitions of what a buffer has to be?
weak acid, it's conjugate.
Yeah. You could also say weak base is conjugate acid. That, but I always say it that way too. Either way works because they're both going to be weak. Yeah. So it has to be weak stuff. So if you ever see a strong acid or a strong base, cannot be a buffer. That's the easiest thing to determine. And then there's one other. All right, you also hit on that because you said conjugate. So the other thing is that they have to be specifically conjugate pairs. And so somebody want to remind me what that means, what it means when something's a conjugate pair.
They can like, we can work with the equilibrium like with each other. Whatever.
That's true. So you're right that there's like only one thing that's different between them.
Plus.
Yeah. One of them has one more H plus. And so, yeah, one of the one with one more H plus is the acid. Once it's donated that, it's acted as the acid and turned into its conjugate base. So that's good. That's kind of review from last unit. And we learned about buffer systems because they're important in a lot of physiological systems. And so, like, anyone who's taking human physiology or a class like that, buffers do come up. I mean, that's a really important thing for how our body controls carbon dioxide, stuff like that. So it is really cool from a medical perspective, but you use it a lot in the lab as well. Basically, it's a way that you can add some stuff to a solution and it lets you add chemicals to it without shifting the pH too dramatically. Because if you didn't have a buffer system in place, you could add a little bit of a chemical and it would like shoot all the way up from pH 2 to like pH 10 in a second. And you don't want that a lot of time. So we also learned with buffers a thing called the Henderson-Hasselbach equation. Probably the most widely used regular thing I've seen since taking this class in other classes. So that's a really good one to memorize. And so this first one is a great example of how you would be asked to use that. So I'm asking you to prepare a buffer. And if he ever asks you a question like this, he might not give you the little like IE that I gave you. So it's good to kind of understand this. But if somebody says prepare a buffer, all they're asking for is the base to acid ratio that's in the parentheses of the Henderson-Hasselbach equation. So see if you can figure this out, spend a couple minutes working on it, and then I'll go over the answer up here. Does anyone want me to rewrite what that equation is? Okay, cool. I think this one is given to you, but you're gonna, it was, okay. You'll do it so many times that you probably won't even need it.
KA, then log base concentration over acid concentration.
Yeah, exactly. And it can be concentration, but you can also use moles as well in these parentheses. So
That's the same.
yeah, yeah, exactly. You have to keep it consistent, and it always has to be base over acid. That's the easiest thing I see people get wrong. And you'll see, I always use moles because sometimes you have to go back to molarity if you want to do that, and it would be useless because they both have the same volume because they're in the same container. So it's like if you divide the same two different numbers by the same value, the ratio of them is still going to be the same. Does that make sense? Kind of.
Like algebra, divide both by.
Yeah, if you have two things that both get divided by the same amount, ultimately the ratio of those two things before and after dividing it will be the same. So you might as well not do that step and use moles. That's why I do that. But yeah, so we have pH given to us. It's 3.62. We have Ka given to us. So how do we get pKa? Negative log. Yep. So negative log of 6.61 times 10 to the minus 4 plus log of base over acid. Let's do this real quick. So it's 3.62 equals 3.18. Then we're going to subtract this on both sides. So I haven't done anything over here. Yeah, haven't done this yet. So I'll get to that in 1 second. So if I said that again, by preparing a buffer, all I'm asking for is give me the ratio of base to acid. I want this component of the parentheses. So we can basically put this in as an X if we wanted to. So how do I get rid of the log over here? 10 to the power of. And it's confusing because you guys did something last unit where it was 10 to the power of minus. That was when you were dealing with a minus log. So don't do that here. If we're canceling out only a log, it's going to be 10 to the power of the positive value. So 10 to the power of 0.44 is going to be our ratio of base to acid, and that gets us an answer of 2.75 as the ratio of base to acid, meaning that they're not equal. If it was equal, the answer would be 1. So think of this as if the answer is 2.75. That means that base is basically 2.75 and acid is 1 because it, again, is base over acid. And so to go back to the very beginning of this problem, I said prepare a buffer. And so this is basically saying that if we have a pH already of 3.62 and we know the pKa, we need to use a ratio of 2.75 whatever base to every 1 whatever of acid. I guess we could say moles. Every 2.75 moles of base we'd add to the solution, we'd add 1 mole of acid. And if we did that, then we would if we did that, we would get to the pH of 3.62. That's what I was kind of getting at there. Does that make some sense? Okay, cool. All right, next one. Now we're getting into some BCA table stuff. And I'll explain how I instantly recognize that. But we have a solution that's made by adding 230 milliliters of 0.2 molarity hydrochloric acid. What's hydrochloric acid? Yeah, strong acid, NHCl, to 400 milliliters of 0.15 molarity NH3. What is NH3? Not hydronium.
Wait, wait.
One is NH3.
Oh,
You're good.
I still.
Weak base? Yeah, you got it. So, oh, you were close. So you were the ammonia.
Ammonia.
You were close.
I don't know what the fuck I heard you say.
NH3 is ammonia, and then once you add the extra H to it to be NH4 plus, that's ammonia. With an M. You're close. You got like a few of the letters right. So again, I know we need to use a BCA table here. How? Somebody want to tell me why I know that?
Given a strong acid, no, I don't know how to say it.
You're right. Yeah. So on the last one, we could go straight to Henderson-Hasselbach because we had, yeah. So if you're ever given one of these problems where you have a weak acid and it's conjugate base given to you, go straight to Henderson-Hasselbach. You're good to go. But in this case, we're given a weak base and only a strong acid. So we haven't formed any of that weak conjugate acid. And we know we need to react away all of that hydrochloric acid, right? Any strong acid or strong base is going to completely react away. So we have to do this. Let's see. And again, this is the stuff that if you can get this down now, the next 2 or 3 classes are really going to be a lot simpler. So we have the weak base. So all I'm going to do is write WB because I don't really care that it's NH3. If you guys can see that. There we go. Weak base, that's our NH3. Plus, I'm only going to write H plus. I'm not worried about the Cl involved. All I'm worried about is the strong acid component. That's our hydronium ion. And this is going to go over here to form, I'm going to say, the conjugate acid. Is that cool? And it would also form water. I'm not even going to write that. We don't care about water. So we start with the B, that stands for before. And so we're going in. And what units do we use for BCA tables? Moles, always moles. So that's easiest way to get the entire problem wrong. BCA tables have to be in moles because we're reacting away exact mole values. Ice tables are the ones that always have to be concentration. So how do we go from molarity to moles? Yep, multiplied by the volume. So let's start with the first thing that we were given, the strong acid. I'm going to do 0.23 liters because we know milliliters don't mean anything, times the 0.2 moles of HCl per 1 liter. Again, that's what molarity is, moles per liter. So we know now by doing this, we're canceling out that liter value. So we're given 0.046 is the mole amount. So we're going to put that here. Now we're going to do the same exact thing for the weak base. So 0.4 times 0.15. You're saying what part molarity?
0.0.
That's moles. Yeah, sorry, let me write the units. So we canceled out liters, right? So we're left with only moles. Yeah, of course. Is that better? So yeah, we need to use moles for a BCA table. So that's what we did here. We can do the same thing with our weak base, the NH3, 0.4 liters times 0.15 molarity. I'm gonna write it a bit quicker this time. And that's 0.06 moles. And then do we have any of this to start? No, we're not told in the problem. So I'm going to put a 0 here. Now, this is the important part of BCA tables that he maybe didn't hit on a ton the other class because this is getting into the next couple classes, but we always are going to react away fully the smaller value. So we have less H plus than weak base. So we're going to fully, this is what we're subtracting. Does that make sense? Okay. So we're subtracting all of this H plus from both sides over here
Wait, why would we?
because it's the smaller value. If it was like 0.07 is what we were starting with, then we would have less weak base to start and we would have to subtract from all of the weak base instead of the strong acid. Is that cool? Yeah. Should I do that wrong? No, okay, that's good. So all I did was, that's a good question. Yeah, so we did this thing down here to go from molarity of HCl to moles of HCl. And so once we have the mole value, this is representing H plus. The reason I didn't write HCl is because Cl doesn't matter. In these problems, you're often going to be reacting away a strong acid or a strong base. All that I care about is the acid or base component. So the Cl can do its own thing.
Say
OH
sodium
minus.
hydroxide or something.
Yeah.
Sodium doesn't matter at all.
Nope, you can put it somewhere else. All I care about would be the OH plus, or sorry, OH minus in that type of problem. So yeah, we only are concerned with this H plus. We're reacting it all away. And that's also going to be reacting with this to form its conjugate acid. So that means we need to add it over here. So 0.06 minus 0.046 is 0.014. We have nothing left of this strong hydronium ions. And we have 0.046 now in the weak acid. And so this is good. We have a weak base left and some of its conjugate acid left. So what do we do next? This is where it gets a little bit more like you have to be really thinking through this stuff. If we have something here and we have something here, we can go straight to Henderson-Hasselbach. So the instance where we would go to an ice table next is if, say, we had none of this left or none of this left. Then we would only have one of those components and we'd need to turn it into molarity and do a whole ice table. And that's what he's going to talk about tomorrow.
The value, starting value and ending value being 17.
No, it's since you have an acid and base.
Since you have both components of the buffer, right? So the buffer we know is, if I told you what parts make up the buffer, you would tell me this, right? It's the weak base and its conjugate acid. If after doing this whole BCA table, so once we get to the after row, we still have some of both of those, that means that we can go straight to Henderson-Hasselbach because we have both components in the whole like plus log base over acid. We have a numerator and a denominator there. So that's is that okay? That's a tricky concept.
Oh, but we're like going to ice table then did.
So this is going to get to tomorrow's lecture for sure. But let's say that's a good question. What if I had 0.06 here also? And so subtracting 0.06 would get rid of both of these, right? Let's think about that. If this was 0 and this was 0 and we had 0.06 here, we would only have that conjugate acid left. And so what I would do is I would take that mole value, put it over the total volume. So that would be put it over 0.23 plus 0.4. So I'd do 0.06 divided by 0.63 liters, and I'd get a molarity value, right? And then from there, I would do an ice table like we did all of last unit, where we're doing the weak acid plus water goes to form H3O plus and its conjugate base, and I would solve for that H plus and it'd be exactly what we did last unit, pretty much. And he'll do that tomorrow. So that was a lot of talking, but you'll get it. So now let's go to the next part. So we have Kb of NH3 given. Can we use that directly? We have to do a few steps, right? If we're using Henderson-Hasselbach, because Henderson-Hasselbach has to be pH equals pKa, a log of a base over acid. So ultimately, we're looking for this thing here, the pH, and I'm going to do negative log of the Ka. So to get Ka, we're going to do the whole Kw over Kb. Again, this part's review from last unit. Are we good with that step? Yes, 10 to the negative 14 is Kw, and we're going to divide that by that Kb. So that means that Ka is 5.56 times 10 to the minus 10. So that's what I'm going to put in here. Right, because if I do negative log of the Ka, we get pKa. Plus log of, and this is important, what's going to go in the numerator? Yeah, so 0.014. Divided by the weak acid, or its conjugate acid, which is weak. And so there we go. We have everything we need. I would try not to plug this straight into your calculator. I'd break it up into this and this and then do that. So you don't make any mistakes. We have pH equals 9.25 plus, let's see what the other part gets us. Plus negative 0.517, meaning it's really 9.25 minus that. So the pH is going to be a little bit more acidic after this, and we're going to talk about that too. The answer here is 8.73 is the pH. And so I always, when I was doing these, would like to make sure that that math makes some sense. And so if we have a buffer where we're left with 0.046 of the conjugate acid and only 0.014 of the weak base, it makes sense then that we're going to go down a little bit, right? It would make sense that if we have more acid than base in the buffer, after we do the whole buffer thing, it's going to decrease in pH because it's going to be a little bit more acidic. But it's not that big of a difference, right? Going from what, like 9.25 to 8.73 is not a crazy drop. So that means we know we're dealing with a buffer system. It's not going down by like 3 or 4 pH points or something like that. Does that make sense? Cool. All right, I spent a lot of time on that one, but that was good. I think that if you're comfortable with all that stuff, you're going to be in a good spot tomorrow. All right, consider the reaction of 20 milliliters of 0.22 molarity, whatever this is. And I gave you a Ka with 14 milliliters of 0.2 molarity KOH. And I'm asking what's the pH of this? So see if you can do this one now using kind of that same method we did up here. We'll give you a few minutes to work on this one.
You know what's the final goal buffer in total?
Like that announcement he sent out.
Yeah.
Is it all that?
Or yeah, you would say, yes, I acknowledge the date change and like you should write down if you can't go get the anymore. The final.
Then what happens to that?
I don't know.
Then?
I say, what if you say no?
Yeah.
I think it's like contact, that's how I can tell, because it just changed date, final.
Yeah, I don't want to scare you guys now, so don't even think about this. But that final, it's not the prettiest,
Bad.
not the best. So
Final.
not the best, yeah. But you guys had an ACS final for Chem 131, right?
We're a
One
See,
so
but you've done it before, so
stayed up all night. I got an 8.89.
that's a great score on ACS final.
That good, really?
For ACS, that's very good, yeah.
That, oh my God.
Yeah.
A week before.
I did not sleep before this one when I took it, yeah. And I got like I also think I need to say that like I got an A minus in this class. So I was not the most locked in my freshman year, and I didn't have Blumling. It was a different professor, and they were like not. Well, I was not as locked in as I would say I am now. An A minus is a great grade. I'm happy with that. But I got like a 79 unrounded on the final, and that was okay.
For next time, I did so good like during it, and then that's the only reason why I literally got a 46 somehow, thought I got like 100, did everything. And I got just enough to pass with like these points.
Oh, that's great. There you go. That's huge.
Like literally just enough, and I was like,
Yeah, I would say like you've been taught a whole lot better than I was, so you're going to be more prepared than I was going into this exam. And if you can kind of at least try a little bit to keep some of the stuff from like exam 1 and exam 2 fresh, maybe like look over it for 10 minutes here and there or something. That'll make studying for it a lot easier, but I shouldn't have said that. Don't worry about it now. You guys will be fine. Let's do this one real quick. So we have C5H5NHCl. There's a few ways that you can figure out what that is, because like when I look at that, I'm not immediately sure, like, is that a salt? Is it an acid? Is it a base? I'm not totally sure. Um, we see that there's an H kind of hanging out loosely at the end connected to a chlorine. Oftentimes, chlorine is going to be something called a counter ion. I don't know if you've spoken about this, but a lot of times to keep something neutral, we throw a chlorine onto it to basically balance the plus that comes from that H plus. That makes sense. That's why sometimes you'll see like ammonium, instead of written as NH4 plus, in a chemical reaction, it'll be like NH4Cl. The Cl is only there to get rid of that plus. So that's what it is in this one. So that's an acid. We also could kind of tell because it's reacting with what? KOH. That's a strong base. So KOH is going to be the thing that is kind of reacting away with this weak acid. So again, I'm not even going to worry about writing out that whole chemical thing. All I'm going to do is do WA for weak acid. And again, I'm not worried about the K, so I'm only going to write OH minus. And this is going to go over here and form the conjugate base of our weak acid. So again, let's do another BCA table. And what units does that have to be? One more time. Moles. Yep. So I get 0.0044 moles for the weak acid. Yeah, of course. No, you're good. So we have 20 milliliters of that solution, right? So it's going to be 0.02 liters times the molarity. So times 0.22 moles per liter. So that's what we need to do for the like train traction 131, right? We're canceling out liters. And so once we do that, we get this answer of 0.0044. That makes sense. We're always multiplying the volume by the molarity. It does. And we don't want it to be molarity. We want it to be moles for a BCA table. Because so this is, I'm writing, this is molarity. So
Oh,
moles over
over
liters. Yeah, exactly. So we got moles because we canceled out liters. So we're left with the moles. We're going to do the same thing over with our strong base.
The point two.
Yeah, that's what we did. Yeah, that's right for the weak acid. And then for the weak base, it's going to be 0.014 times 0.2. So that's going to be 0.0028. And again, we're assuming we have nothing of the conjugate base to start. So what value are we subtracting from here? Did I do the math wrong? I got 0.208. 0.014 times 0.2. Yeah, I got 0.0028, not 0.008. You're good. So you're right though. We're subtracting by the smaller number. Yeah. So we're going to subtract away all of the strong base component. So that's going to be this guy here. And again, that's going to be removed from our weak acid. But since it's a base reacting away, as it reacts away with that weak acid, we're forming the weak base. So we're going to be adding it over here. So we do that in our calculator real quick. We get 0.0016, nothing for the OH minus because we reacted all that away, and 0.0028. So again, we have both components of the buffer, right? In the after row, we have both the weak acid and its conjugate base. So we can go straight into what? Henderson-Hasselbach. Yep. That's the clue in, right? We need to have both of these to do that. And when you can do that, always do that. It's way faster. So let's see, we're given Ka. That's nice. We don't even need to convert it to K from Kb to Ka. So it's going to be pH equals negative log of that Ka. Again, because we need it to be pKa. And then what's going in the numerator here? Log of what over what?
base over acid.
Yep, 0.0028. Yep, you both got it. And if you don't want to do the whole decimal stuff, you could also do 28/16. It's a ratio. It's going to give you the same answer. So it's a little tip if you want it. And over here, this is going to be 0.0243. And the pKa is going to be 5.23. So our final answer is going to be 5.47. And again, real quick, does that make sense that we're going from a pKa of 5.23 to now 5.47? It should, because we're adding what? We're adding strong acid, right? That's what's reacting away. So once we've added that, it would make sense that this value is going to go up a little bit. We've got a little bit more basic. You could also tell that because after we've done the whole BCA table, we have a little bit more base than acid. So this number should be adding instead of subtracting. So a few ways to kind of make sure your work looks good. Okay, do we feel good with Henderson-Hasselbach stuff? Okay, cool. Then this is a good one too. This is another Henderson-Hasselbach, so we'll do it pretty quick. This one should take a couple seconds, but it's a good like conceptual review. In fact, some of you already know this. I didn't. I have to type in my calculator still. You might even be able to do this one without using a calculator. So it's kind of a clue. Does anyone know what log 1 equals? 0. Yeah, it's okay if you don't know that. I had to look it up. So log of 1 is 0. And so anytime the ratio of base to acid is 1 to 1, so right, it's 1 to 1 here because they're both the same molarity. It's 0.5/0.5. That's the same as 1 to 1. Then your plus log component is going to be plus log of 1. So that's going to be 0 plus 0 overall. So what's the answer here? It's the pKa. So this pH is equal to pKa. And that's a good conceptual thing to know, is that if your base to acid ratio is equal, pH equals pKa. 4.76. Yep. Cool. This is another one that you don't need to use a calculator for, more conceptual, but it's kind of helping you understand how scientists might make a buffer system. So I'm saying you need to prepare a buffer with a pH of 7.4. And I have listed a few acid-base pairs, and I'm asking which one would be the best for making this buffer system. Yeah, that's it. So in this case, acetic acid and its conjugate base acetate are in the 4 to 5 range. If we go straight to C, ammonium chloride and ammonia is in that 9 to 10 range. Phosphate and sodium phosphate is 7.2. That's pretty close to what we want to get, and that's 7.4. So if this was a thing on your quiz, it'd be an easy freebie, but all you're doing on these ones is you're looking for the closest pKa pair to the pH that you want to get to. Does that make sense? Cool. All right. Now, honestly, I probably should have ordered these the other way around, but you should be able to get this now. Let's go one by one and tell me, would this be a buffer system or not? How about the first one?
No.
No, for so many reasons, right? We're dealing with a strong base on the right side there, calcium hydroxide, and they're not conjugate pairs. So how about the next one? Yes, right? We have HF and NaF. NaF is the conjugate base, and against sodium, the Na is there as the counter ion. So it's kind of balancing the F minus. So that one works. We're on B. So yeah, HF and NaF. There might be multiple answers on this one. So I think there are. Let's keep looking. Next one. No, right? How come? Strong acid, and this is a salt. Um,
That's cool.
yeah. So this one here, how about this? Oh, okay. Yes, the answer is yes. This one is. So the K for the other part is the counter ion. So this is acetic acid. No, this is a carboxylic acid, whatever. Who cares? And carboxylate anion, whatever. Um, Next one. What about this one? Also, yes. Yeah, this is acetic acid and an acetate.
We're just
Uh,
looking.
Sorry, this is acetate, this is acetic acid. Yeah.
Yeah.
Yeah. And then how about this last one? No, this looks horrible. And here, this is a strong acid. So no. Do we feel good with that?
We don't want.
If you ever see a strong acid or a strong base, no, it cannot be a buffer system. So yeah, a lot of the rules and stuff that you learned in the last unit, still very important for this unit. And you'll see that again tomorrow. Like we're going straight back to ice tables. So, um, let's see, do we want to do this one? Uh, nah. This one's Henderson-Hasselbach. If you could do the other ones, you can do this one. Does anyone want to do the practice? Feel free to raise your hand. Okay, cool. Yeah, all you have to do on this one is we have an acid and its conjugate base. This is a buffer system, so it's going to be pKa plus log of this over this, and that's the pH. Then this is the last one. I think let's do this one. This one is good because it's like kind of a conceptual review of what even is the point of a BCA table. What are we looking for? That sort of thing. So if a buffer contains equal concentrations of ammonia and ammonium chloride, first off, equal concentrations, that's again a ratio of 1 to 1. So that would be the pH is equal to pKa. Good thing to review, but that's not what I'm asking. If a small amount of strong acid is added to the solution, so say we added some HCl, what would happen to the pH? You sure about that? If we started adding strong acid to something, it would be better than if we didn't have a buffer. You're right. It will go down. So that's the answer. It would still decrease. The pH would decrease if we added hydrochloric acid, but it wouldn't decrease a lot. So that's the whole point, is that buffer systems are not perfect. There's still going to be some shift in the pH value, but instead of being like dramatic, going from like 14 all the way down to 1, it's going to be more like. So that's a good question. What is an acid? Is it a high or low pH? Low. So if we have a buffer system and we start adding a strong acids again, those are like 1 to 2. It's gonna go down with it. Yeah. Yeah. No, that's a good question. So yeah, the first one, the answer to A is it's gonna decrease, but only a little bit, maybe like 0.3, 0.4, something like that. Which component of the buffer will react? Do we think it's gonna be ammonia or ammonium chloride? Ammonia. Yeah, how come? Yes, so ammonium has a hydrogen, meaning that's the weak acid component of the buffer. We're looking for the weak base component. That's what's going to react away with the HCl. So the ammonia is the NH3, and that's what's going to mix with the H plus to form more of that NH4 plus, the ammonium. Cool. We're good with that? Sweet. Last part, describe whether the buffer capacity is increased, decreased, or unchanged. It's decreased, right? So if at first it's a 1 to 1 ratio, that's a pretty good buffer capacity. And what buffer capacity means is like, how good is it at resisting a change in pH? Higher the buffering capacity, the better it will be at staying kind of like at a very similar range. The lower the buffering capacity, it's not doing great. So if we start reacting away some of this guy, well, all of a sudden the ratio is going to be more acid and less base. So that log of base to acid, instead of being log 1, it's now going to be something like log, I don't know, 0.25 or something. And that's going to be lowering the pH a bit. So it's not going to be as good. That makes sense? Cool. All right. If any of you guys have any more Henderson-Hasselbach type questions or BCA table, feel free to stay after.